In this video, we're going to take a little pause out of our linear graphs and coordinate geometry, and we're going to be looking at function notation. And function notation is a really important part of the Maths Methods course. It is the way we refer to functions frequently throughout the entire course. Okay, so usually it's a Maths Methods topic. However, it's also really useful when you're working with your CAS. So if you can understand about function notation and how it works, it will make a lot of the work that you do with your CAS potentially more efficient if you get used to using function notation in your CAS as well. Okay? And then that's also going to reinforce that mathematical understanding of what you'll be writing on paper, along with that supporting you being able to work efficiently with the CAS. So we saw the function notation in the previous video when we were looking at linear graphs and sketching graphs with our CAS, okay? And we saw that our CAS uses f1 of x, f1 brackets x equals in place of y equals for the graphs, okay? And this is function notation. It is saying, as I said to you in the previous video, f1 of x. It's function 1, which is in terms of x, okay? Function notation, as I said, is taught and used in Maths Methods course from next year, but a basic understanding of it now will help you to establish a better use of your CAS early on. Okay. So a simple equation, such as y equals 2x plus 1, can be thought of as having input and output. Any equation, any function, well, not all equations are functions, that definition we'll leave until next year, but any function can be thought of as having input and output. And when we use x and y, x is the input and y is the output. So what we have here is we have our input x, and then we double that input and add 1 to it to produce the output y. Okay? So we take x values, we stick them into our special kind of function named f, and this function is double and add 1. We double all our input values and we add 1 to them, and we produce our output values. So the output is completely dependent on the input. The y value that we get completely depends uniquely on the x value that we put in. And so we can sometimes talk about dependent and independent variables. We would say that this is the independent. We can put whatever x value we want in, but the y value, what can't be anything, it'll be dependent on what the x value is. Okay? Now, the y value is a function of the x value, okay? This depends on the x value. It's completely connected to and related to the x value. So we actually don't need a separate letter for this. We don't need to call this y. We can just talk about this as being a result of applying this function to this value, f of x. We did f to x and we got 2x plus 1. And we read that as f of x, okay? So f is the function that will convert x into 2x plus 1. So that means that we would say that f of x is equal to 2x plus 1. Applying f to x, we get 2x plus 1. F will convert 2 into 2 times 2 plus 1, double and add 1, to give 5. So the statement we get from this is that f of 2, applying the function f to the number 2, to the input value 2, gives 5. Okay? F will convert negative 1 into 2 times negative 1 plus 1, which is also negative 1. So the interpretation of this is that f of negative 1, we apply our rule f to the input value negative 1, and we get negative 1. Okay? In this one here, we take our function f, we apply it to the number 3.5, we do f to 3.5, that is we double 3.5 and add 1 to it, and we get 9. Okay? So we have this general statement of the rule, f of x is equal to 2x plus 1, but then we can do that for specific values. F of 2 would be 2 times 2 plus 1, which is 5. F of negative 1 would be 2 times negative 1 plus 1, which would be negative 1. F of 3.5 would be 2 times 3.5 plus 1, which is 9. Sorry, it's not 9, is it? 2 times 3.5 is 7, plus 1 is 8. Sorry, can we correct that? So that should be 8 in the notes, and f of 3.5 is 8. When using function notation to refer to a function that doubles the input and adds 1 to it, as I said, we would write f of x is equal to 2.2x plus 1. Applying function f to the input value x is gives 2 times x plus 1. And as I said, we read this as f of x. We would read this as f of 2, f of 3, f of 7, f of negative 1, whatever it might be. Let's consider a different function. We're also going to call this one f, but they don't always have to be called f. Okay? So let's have another function. This one's also called f, where f takes the input and it multiplies it by 3 and then adds 4. Okay? So if our input is x, f of x, doing f to x, is taking x, multiplying it by 3 and adding 4. So f of x equals 3x plus 4. If our input is 2, f of 2, so doing function f to 2, means taking 2, multiplying it by 3 and adding 4 to it. So it gives 10. F of 2 is equal to 10. F of negative 4 means applying function f to the input value negative 4. So we're doing 3 times negative 4 plus 4, which is negative 8. So f of negative 4 equals negative 8. 5a, if the input is 5a, we're doing function f to 5a. So we're taking 5a, we're multiplying it by 3, and we're adding 4 to it, which gives us 15a plus 4. So f of 5a, applying function f to 5a, gives 15a plus 4. Okay. These are essentially the y values. When x equals 2, y equals 10. The input is 2, the output is 10. When x equals negative 4, y equals negative 8. When the input is negative 4, the output is negative 8, etc. Okay, as I said, we conventionally use the letter f as the name of the function, but any letter or symbol could be used. So, for example, we have another function here in this first table, function g. Function g is that we do 7 minus 4 times the input. Okay, so let's complete the table here. So if our input is x, g of x, doing g to x, is doing 7 minus 4 times x. Okay, that's what our rule for g is. So if we want to do g to 1, we're doing 7 minus 4 times 1. Okay, so we're replacing the x's with 1's. The input, i.e. the x values, become 1. Okay, and 7 minus 4 times 1 is 3. So g of 1 equals 3. When x equals 1, y equals 3. Alright, again, g of negative 2 means doing 7 minus 4 times negative 2, which is 7 plus 8, which is 15. So g of negative 2 equals 15. When the input is negative 2, the output is 15, i.e. when x is negative 2, y is 15. The graph goes through the point negative 2, 15. All those things are the same. Okay. When our input is x plus 1, we're going to apply rule g to that input. We're going to do 7 minus 4 times g plus 1. So it's going to be 7 minus 4 times, not g plus 1, sorry, x plus 1. So that is 7 minus 4x minus 4, which collecting like terms is 3 minus 4x. So the input doesn't just have to be numbers. Okay, function h on the right hand side here in the second table. Sorry, I didn't mean to hit the microphone there. Function h is the square of the input plus 5. So we're going to square the input and add 5. So if our input is x, applying rule h to x, i.e. h of x, doing h to x, is to square the input, so square x and add 5. So we get h of x is equal to x squared plus 5. If our input is 2, okay, we're doing h to 2, so we are squaring 2 and adding 5. Okay, so we're going to get 2 squared plus 5, which is 4 plus 5, which is 9. So h of 2 is equal to 9. When the input is 2, the output is 9. When x is 2, y is 9. The graph of h would go through the point 2, 9. All of those things say the same thing. Okay. When our input is negative 3, h of negative 3, applying rule h to the number or the input value negative 3, means that we take negative 3 and we square it, and then we add 5. Those brackets are really important there with that negative. Remember, we've talked about that before. Negative 3 squared is not the same as negative 3 all squared. So be careful what you write. Make sure you write what you mean. Negative 3 all squared is positive 9 plus 5 is positive 14. So h of negative 3 is equal to 14. That is when the input to h is negative 3, the output is 14. That is when x equals negative 3, y equals 14, i.e. the graph of h would go through the point negative 3, 14. And finally here, when the input is 2x, applying rule h to 2x, we take 2x, which is the input, and we square it and we add 5. 2x all squared is 4x squared plus 5. Okay, consider the functions f of x equals 1 minus 2x and g of x equals 3x plus 5. So the first question, part A, wants us to work out f of 3. So we're changing the input, changing the x values to be 3. So the rule becomes 1 minus 2 times 3. Sorry, I didn't write 1. 2 times 3. We're making the x values 3. The input becomes 3. We're doing 1 minus 2 times the input. So if it's f of 3, the input's 3. 1 minus 2 times 3. So that is 1 minus 6, which is negative 5. G of 0 means this time we're using g of x and we're making the input 0. X becomes 0. Okay, so if x becomes 0, we're going to replace the x's in the equations with 0 and we get 3 times 0 plus 5, which is 5. So g of 0 is 5. Okay, f of x equals 0. Okay, so the rule tells us that f of x is equal to that. That is f of x. Okay, 1 minus 2x is f of x. So this time we're not letting x equal 0, we're letting f of x, the output, equal 0. So 1 minus 2x has to equal 0. Add 2x to both sides, 1 equals 2x, and divide both sides by 2, x equals 1 half. So when the output is equal to 0, when if we apply the function f to an unknown input and get 0, we can work out that that input must have been 1 half. Okay, the x, in order for the output to be 0, the input has to be 1 half. Whereas here, the question is, if the input is 0, what is the output? Okay, the output is 5. G of x equals 11. Again, that is g of x. Okay, so g of x is equal to 3x plus 5. So if we want g of x to equal 11, that is 3x plus 5 equals 11. Subtracting 5 from both sides, 3x equals 6, and dividing both sides by 3, x equals 2. So what we've worked out is that the input must have been 2 in order to give an output of 11 for the function g of x. Okay, part E is f of x equals g of x. So we know that f of x is equal to 1 minus 2x, and we know g of x is equal to 3x plus 5, and so therefore 1 minus 2x is equal to 3x plus 5. And we can solve this for x. Let's add 2x to both sides to get 1 equals 5x plus 5. Subtract 5 from both sides, so negative 4 equals 5x, and divide both sides by 5, so x is negative 4 divided by 5, negative 4/5. Okay, so when we have an input value, when x is equal to negative 4/5, both f and g will have the same output. They will be equal to each other if x equals negative 4/5. Okay, so let's go back to where we first saw the function notation, which was with our CAS. So as we saw, when we plot a graph with our CAS, we are defining a function. Okay, so when I draw the graph, let's stick with the one that's in the notes here. So I've used the scratch pad button to get over to the graphing screen. I currently can't see the entry line, so I'm going to press tab, and it says f1 of x. And when I draw the graph 7x minus 3, I automatically define a function in my CAS. My CAS now understands that if I type f1 in the calculator screen, I am referring to the rule 7x minus 3. Okay, so if I go over to my calculator and I type f1, you'll see the minute I typed f1 it went bold, and that's because it's telling me that it's referring to a stored function. If I just type f1 of x and press enter, it's telling me that f1 of x, according to its memory now, is 7x minus 3. Okay, so if I want to do f1, I'm looking at part A here. If we do f1 of 0, f1 bracket 0, we've just been doing this. What we're doing is we're replacing the input in our function with 0. We're replacing all the x's with zeros. We can do that algebraically. It's 7 times 0 minus 3, which is going to be minus 3. Let's see if our CAS confirms that. So I'm just going to write that underneath. Yep, our CAS confirms that f1 of 0 equals negative 3. Now, thinking about the graph, okay, so we were drawing a graph, and we just let x equal 0. So what feature of that graph have we found? If we let x equal 0 in the graph, and we find that the function equals negative 3, that's the y-intercept. Because we found y when x equals 0. That's what we just did. Okay, we let x equal 0 by typing f1 of 0. Now, I know for a linear graph, finding the y-intercept is easy. We could see it there, we could tell it was negative 3. But again, let's think about these as strategies for all sorts of other graphs. If I've sketched a graph f1 of x on my graphing screen, and if I type f1 of 0 in the calculator screen, I'm letting x equal 0, and so I'm therefore working out what the y-intercept is. If I were to solve f1 of x equal to 0, okay, so this time, f1 of x is that. So solving f1 of x equal to 0 is solving 7x minus 3 equals 0, which we can do by hand. 7x equals 3, x equals 3 on 7. So what we've done is we have let y equal 0, and we've found the x-intercept. So x-intercept, we found x when y equals 0. Okay. Now it's important to understand that in your CAS, if you just type f1 of x equals 0, it's just going to give you the equation, 7x minus 3 equals 0. So because we actually then have to, once we get the equation, we have to solve it, we actually want the CAS to solve f1 of x equals 0. So menu 3, 1, solve. I don't need to type it again if I've typed it before. I can just scroll up here to this bit, which is what I want, and press enter to copy that into the next line, and then comma x, remember, for solving. So solve that equation for x, and it gives me what I got by hand, which is x equals 3/7. But in terms of, in the context of the graph, what we've found there is the x-intercept of that graph. If we were to calculate f1 of 3, let's do that by hand first. So f1 of 3 is letting the x value, replacing the x value with 3. So f1 of x is 7 times x minus 3. f1 of 3 is 7 times 3 minus 3. So that is 21 minus 3, which is 18. Okay. So what does this tell us about the graph? Okay, so when we did that, we let x equal 3, sorry, and found that y equals 18. Okay. So in terms of what it tells us about the graph, it tells us that when x equals 3, y equals 18, which means that the graph passes through the point (318). And again, we could get our CAS to do that for us. I'm not asking you to do it by hand. f1 of 3, let's confirm that it gives us 18. Indeed it does. Okay. So making use of the function notation defined by your CAS is a quick and efficient way to find key features of graphs, particularly once we get beyond linear graphs. Once we get into our parabolas and cubic graphs and lots of other graphs that we'll look at, particularly in semester 2, this is going to be a really important strategy for being able to work efficiently with our CAS. Okay, the work today is from a worksheet, so some practice of function notation by hand and establishing an understanding of that, but also some questions about, utilising the functions when they get defined in your CAS when you draw a graph.